Hi, hello friends, welcome to my channel. My channel name is Chemistry Coaching for EAMCET MSC CSIR UGC NET. Here I am providing videos for intermediate students, BSc students, MSc students, PhD students. Present video is very useful to PhD students. In this video I am discussing how to synthesize 1,3 polyols. So let's get into the video. So this is a seminar given by me in my PhD. So the seminar name is Stereoselective Synthesis of 1,3 polyols. So here I am discussing synthesis of 1,3 polyols by using different methodologies. So how in the literature how 1,3 polyols are synthesized. So I am discussing here. So the contents. So here in the seminar, the contents are introduction, epoxide opening reactions, ancillary stereo control, Evans reaction, 1,3 and 1,5 stereo control reactions, asymmetric allylation, Prince cyclization, oxymercuration of homoallylic alcohols, tandem intramolecular silyl formylation, allyl silylation. So 1,3 polyols or motif is very common in polyene macrolides. So why in generally we are synthesizing polyols, or why we are developing 1,3 polyols? So in general what will happen? In generally we will choose a target molecule. In the target molecule we will observe the functional groups. So like 1,3 polyols or suppose 1,2-diol or methyl hydroxy are adjacent, or polyketides like. So we will see what are the functional groups in the molecule. So we will choose a target molecule. So in the target molecule we will found the functional groups. So based on the functional groups we will develop the methodologies. Suppose if a molecule having a pyran ring, so people will develop a methodology how to do a pyran ring. Suppose it is having a furan ring, so some scientists will develop how to do a furan ring. Some people, some molecules are 1,3 polyols, so people will develop how to synthesize 1,3 polyol. This is happening in the method development. So first I am showing here some molecules which are having 1,3 polyols. So please here go through the structure. Just I am showing one structure. So you see roxaticin. So here 1,3 polyols are there. So 1,3 polyols. So in every structure there is 1,3 polyols. So in the sense 1,3 hydroxy. 1,3 hydroxy groups are present. So these molecules are finding the nature and having a lot of activity. Suppose amphotericin B is having antifungal activity. Because of this activity, people are synthesizing this molecule. So while synthesize the molecule, they will develop the method. So first we will go to discuss about epoxide opening reactions. So in epoxide opening reactions, first what we will do Sharpless kinetic resolution. Then we will treat the epoxide with Redol. So what will happen is the Redol will open the epoxide from this position, second position. The hydride will attack here, this star position. So you will get a 1,3 alcohol, 1,3-diol. So this methodology is developed by user Casey Nicolo. So this is the Redol structure. So this is the methodology, okay, developed by Kishi. So you see here radol selectivity. With radol you are getting 1,3-diol is 100:1, 100:1, 125:1, 100:1. So this is the transition state. So what is happening is the hydride will attack at second position. The hydride attack at second position. So then you will get 1,3-diol compound. This is the methodology developed by Kishi, and this methodology is used by Casey Nicolo for synthesis of this 1,3-polyol moiety. You see here, if you treat the reaction with dibol, so dibol ester is converted into alcohol, and alcohol is protected as the O-polyol using polyol chloride, triethylene DMAP. And either with dibol treatment, this epoxide is open, you are getting alcohol. This is protected as a O2-PDPS. So then you treat this compound with dibol, you will get alcohol here. Then you subject it to Sharpless asymmetric epoxidation, followed by radol opening, you will get 1,3-diol, this compound. So first you are doing here Sharpless epoxidation, followed by radol opening, you are getting 1,3-diol. So you are doing functional group manipulations to get these two fragments. These two fragments are used in the synthesis. So here our target is how to synthesis 1,3-polyols. So here just you see here, first Sharpless epoxidation, followed by radol. So we need these two steps. So first we are doing Sharpless epoxidation, followed by radol treatment. So this is the methodology used by Casey Nicolo in the synthesis of the structure. So then we are going to ancillary stereo control. So ancillary stereo control is a very simple methodology. In general, what will happen is a stereo center is adjacent to carbonyl. So carbonyl adjacent to carbonyl, it is prone to go epimerization. So if you treat the center with K2CO3 methanol, so what will happen is the center is here is having a lot mixture or in racemic form. So it will convert it into exclusively one compound. Why? Because of this compound is in cyclohexane form. So on the cyclohexane form, the group in which is in axial position will go to into equatorial position when you treat with K2CO3 methanol. Because of that stability, you are getting the unwanted compound is converted into wanted compound, exclusive one compound. So this is developed by Gilbert Stark. So this methodology is simple. So we are using here epimerization. Epimerization we are using. So because of this, suppose you see here, the center is alpha to carbonyl. So if you treat with the K2CO3 methanol, what will happening is it will coming to equatorial position. So we are treating the compound, we are racemization is taking place, then it coming to equatorial position. So this is because of this 6-member ring is forming cyclohexane chair conformation. In the chair conformation, the axial group is converted into equatorial group. So this is the trick here using by Gilbert Stark. So he is using epimerization very cleverly in the cyclohexane. So here the same step. You see here this stereochemistry here is 1:sin. If we are treating the K2CO methanol, here I am showing the chair conformation of this 6-member ring. So the one of the aldehyde is at hydrogen at axial position. When you treat the K2CO3 methanol, so here racemization taking place, the group will occupy into equatorial position, the hydrogen will come axial position. So here the 1,2 here syn chemistry is coming to anti. So this is the methodology used in the synthesis of this molecule. So here the trick is very simple. We are using epimerization in the 6-member rings. So here we are treating You see here this step is very important to us. So first we are doing is ozonolysis, and we are getting aldehyde. So at this center, the center is in racemic form. So what we are doing is we are treating with K2CO3 methanol. So once if you subjected to K2CO3 methanol, what will happening is, so the required syn chemistry is appearing here because of the ring already we discussed in the previous slide. So here the racemic center is converted into wanted up or down center depending on the chair conformation. So this methodology used by Renowski. So this methodology used in the synthesis of mycotoxin. So in the same way, Renowski used reductive decyanation of cyanohydrins. You see here, first Renowski what is doing is having TMS cyanide. So what will happen? You will get cyanoalcohol first. Then the diol is protected using acetone CSA. You will get syn-anti 1:1. So what is happening is he is doing alkylation with the LDA. So doing the alkylation with the LDA, what will happen is the unwanted syn-anti mixture also converted into exclusively syn isomer. So why the reason already we discussed in the previous slide. So the one of the anti-isomer the group is racemization taking place. In the wanted group we are getting syn isomer exclusively, and he is removing cyano group using sodium liquid ammonia. So he is getting syn isomer exclusively. So here Renowski used this methodology very in the same way. So first he is doing preparing this cyano compound, and he is doing alkylation using LDA one side. So first alkylation is taking place in the first step. In the second step also he is taking the same cyano compound and again doing the alkylation. So after doing two alkylations, so what is happening? He is removing cyano. So he is used this methodology in the synthesis of roxaticin. So next we are moving to Evans reaction. In the Evans methodology, what is taking? He is taking alpha, beta, gamma, delta hydroxy alpha, beta unsaturated ester compounds. So in the presence of base, what is happening in the presence of base? Here anion will generate, it will add into benzaldehyde. So you will get a anion here. It will add on to this beta position of alpha beta unsaturated esters. Because of we are getting syn compound exclusively. The reason is very simple. Here also we are the reaction is going through 6-member chair conformation. Because of a favored chair conformation, so you are getting exclusively syn compound as the major product. So see here, if you take a trans compound and you will treat with tertium butoxide. So first in the equilibrium position, the ring will broken, and you will get exclusively the anti-compound also 1,3 anti also converted into 1,3 syn. So in the same way, if you treat this is happening. This is because of equilibrium. So we are converting 1,3 anti into 1,3 syn compound. Okay, next we are going to in the 1,3 and 1,5 stereo controlled reactions. So first we will discuss about 1,3 syn reduction. So in the 1,3 syn reduction, first we will take beta hydroxycarbonyl compounds with tributyl boron and sodium borohydride. So we will get 1,3 diol as the major product. So here 1,3 syn chemistry is happening. So if you go to the mechanism, the reason is simple. In the first hydroxy keto form a 6-member ring, chelation is forming with boron, and the hydride will attack from bottom phase because of this butyl group is occupying axial position. Because of that way, hydride ion will attacking from the bottom position. You are getting exclusively 1,3 syn diol as a major product. So this methodology is actually developed by Narasaka et al. So replacement of one butyl group with OME group and so with sodium borohydride result developed by this methodology is developed by Evans. So if you take this beta hydroxy ketone with hydride reagent, then you are getting syn as the major product. So this is the syn reduction. So you see here with lithium iodide LAH you are exclusively getting 9505. So you are getting 1,3 syn reduction as the major product. This methodology also used with the lithium iodide LAH. This methodology was developed by Arun Ghosh. So if you treat this beta alkoxy carbonyl compounds with the lithium iodide followed by LAH, so you are getting 1,3 syn compound as the major product. So this methodology also same. First lithium iodide chelation is taking place, then the hydride ion delivery from bottom phase results in 1,3 syn compound as the major product. So this methodology used in the synthesis of this molecule, this compacting lactone. So 1,3 anti-reduction. So in 1,3 anti-reduction, if you treat the beta hydroxy carbonyl compound with a tetramethyl ammonium triazoxyborohydride, you will get 1,3 anti-stereochemistry as the major product. So if you treat the mechanism here follows. First what will happening is the reagent will form a chelation with this hydroxy compound, and the hydride ion delivery from this phase results 1,3 anti. So this is a methodology developed by Evans. So here we are using tetramethyl ammonium triazoxyborohydride for 1,3 anti-reduction. So in the same way 1,3 anti-reduction we will use samariamide also we will be using. Using samariamide also you will get 1,3 anti-stereochemistry. So if you want to synthesis 1,3 anti-diols, you can use samariamide or you can use tetramethyl ammonium triazoxyborohydride. And another methodology for synthesis of 1,3 polyols, first we have to treat dithiene with the butyl ether. You will get anion here. So this anion will add on to epoxide. So the epoxide is opened with this dithiene. You are getting this compound. Then then we can remove the thiol group using methylated calcium carbonate, and we will treat with the sodium borate followed by diethyl boron OMe. You will get the required compound. So the reason is here simple. So we are repeating same functional group manipulations, and we will prepare the epoxide using standard methodology. Like first we will convert the primary group into tosyl chloride, followed by treating with base, you will get epoxide. So then the epoxide is opened with one more time with this dithiene group. Then we will get this compound. Then the sequence of reactions are same. First we will remove the dithiene moiety, then we will do reduction, 1,3 reduction, and we will put a estenide. So this is the methodology. This methodology we are also used. We are also means I also used in the synthesis of polyhactide A and polyhactide B. So that is the one methodology. So another methodology is 1,3 asymmetric induction. So this is called Mukayama order. So what we will do, we will protect the enolate in the form of 40MS. We will add enolate to aldehyde having alpha beta gamma. So in third position there is a OPMB or OTBS or Cl group is present. So in the presence of BF3 etherate, we will get exclusively anti-stereochemistry. This is very important. If we add this enolate in the presence of acid, you will get exclusively 1,3 anti. So here they proposed Mukayama order also proposed different transition states. But here we have to note that first we are getting 1,3 anti. So here lot of transition states proposed, but I am not going to the details in the transition states. So here you can use this methodology cleverly if you want to synthesis. So we will go to 1,5 asymmetric induction. So here see already your enolate is protected with enolate is prepared using dibutyl boron trifluoride. Here there is a alkoxy position. If you add this enolate to aldehydes, you will get 1,5 anti as the major product. So 1,5 anti as the major product. So the corresponding transition states here they are provided some. So according to this one, 1,5 anti is the major product. So here the empirical rule is, if you have a aldehyde, if you add a aldehyde and if you add a boron inlet, you will get 1,5 anti. So we are we are using this methodology in the synthesis. So if you are treating with this keto compound with dibutyl boron triplet, first we will generate suppose here enolate, then we will add a aldehyde. Exclusively we are getting 1,5 anti. You please see here. So in the same way, if you treat with dibutyl boron triplet with this aldehyde also, you are getting 1,5 anti. So here the thumb rule is, your starting metal should have a alkoxy at third position, and if you add aldehyde, you will get 1,5 anti. The directing group here having your substrate here. So then we will go to asymmetric allylation. So if you take asymmetric allylation, this is a Brown's asymmetric allylation. If you take benzoaldehyde and you will subject it to beta allyl diisophenyl camphenyl boron, we will get the homoallylic alcohols. Based on the here, if you take the reagent, according to the reagent you will get selectivity. So this is called Brown's allylation. So based on this Brown's allylation, some people are synthesized in the synthesis of passive fluorine A. So if this can use in the synthesis of passive fluorine A. So what is happening here, a lot of groups are 1,3 polyols are there. So first what you have to do, you have to do 1,3 Brown's allylation followed by production. So then followed by same way vaginolysis, followed by Brown's allylation, followed by production. Then vaginolysis, Brown's allylation, followed by production. So you have to do iterative steps. Iterative means continuously. So according to required stereocenter, you have to change the catalyst. So this is the methodology developed by Brown's. So then we can generate 1,3 polyols using Prince cyclization. So if you take this homoallylic alcohol and you treat it with crotonaldehyde in TFA, what will happen? You are getting is a Prince cyclization is taking place. So if you want the methodology, please go to the Prince cyclization methodology. Then we are treating with sodium liquid ammonia. With sodium liquid ammonia, double bond migration is taking place, and you are getting this compound 1,3 anti-diol. So once you have to subject the diol with vaginolysis followed by 1 carbon wetting, you are getting this compound. So then you are repeating one more time Prince cyclization. So once you are getting Prince cyclization, you will get the pyron ring. So once you break the pyron ring, so first you are doing mom production. So mom production will take place here and here. Then you treat it with mom chloride, mom production followed by sodium liquid ammonia. The ring will broken and you will get here this compound. So we are doing here Metsunobu inversion. Metsunobu inversion followed by mom chloride production. You are getting this compound. So we can use this molecule in the synthesis of this compound. So this methodology developed by Jadhav et al. So they are using for a Prince cyclization for the synthesis of 1,3 polyols. So then oxymercuration of homoallylic alcohols. So if you take like this is EAMCET methodology, like it will follow the same way. In the if you take homoallylic alcohol and you will are treating with this carbonyl compounds and followed by HgClOAc. So you are getting 1,3 polyols, 1,3 syn chemistry. So mechanism as follows same way. So in the presence of acid, the alcohol will add into carbonyl compound. You will get a chelation with this catalyst, and the mercury will forming here 3-membered ring with a double bond, and this oxygen will adding onto this double bond, and you are getting this mercury compound. So this is like Evans reaction. So if you using this methodology, mercury chloride is converted into aldehyde using above condition like rhodium, HCl CO2, and corresponding phosphine hydrogenation carbon monoxide. So this methodology is developed by LinkedIn. So you can prepare this same conditions for preparation of 1,3 polyols. So you see first here you are taking this homoallylic alcohol and treating with event template. So first you are getting 1,3 syn mercury, then the mercury is converted into aldehyde. So then you are stepping some brown cellulation, you are getting brown cellulation, you are getting the homoallylic alcohol. Then we are repeating the same steps. So step reagent 1, reagent 2, reagent system 3. So you are getting the 1,3 polyols. So this moiety is used in the synthesis of molecules. This methodology is developed by LinkedIn. So finally, I am going to discuss a tandem intramolecular silyl formulation and allyl silylation. So you have to prepare this compound with you see here silyl is having 2 allyl groups. So in the presence of rhodium macaque CO2, carbon monoxide benzene, hydrogen peroxide, sodium bicarbonate, you are getting 1,3 polyols. So here the mechanism is very complex. So you see this allyl grouping is transferred to here. So you are getting first this silyl O-allyl compound. Then this compound will break. You are getting this 1,3 polyols. So this mechanism is very typical. So please go through the mechanism. But here I am suggesting to prepare 1,3 polyols, but I am also not familiar with the mechanism. You can go through the mechanism by using this paper, Jack's paper. So synthesis of mycotoxin. So LinkedIn used this methodology in the synthesis of this compound. He treated the homoallyl alcohol with event template. First he is getting mercury. So then mercury is converted into aldehyde, followed by treating methyl grignard, followed by DMP oxidation. He is getting fragment A. So in the same way, he also preparing fragment B using rhodium macaque. So if you take this homoallylic alcohol and treating with LinkedIn methodology, you are getting 1,3 polyols. Then the 1,3 polyol is protected with 2,2-DMP CSA. Then the estanoid protection is taking place. Then he is doing oxymercuration by formulation. So oxymercuration formulation previous methodology. So you can use event reflect HgCl OSC followed by formulation with rhodium macaque reagent. So you are getting aldehyde. So this aldehyde and they are his A and B coupled using see here A and B is coupled here, and he is getting this fragment. This fragment is used in the synthesis of mycotoxin. So here these are the available synthesis of 1,3 polyols I collected from the literature. You can use this methodology if you want in your synthesis. So these are the references. If you read oxypolyol macrolide antibiotics by Scott and M.Sc, you will get the information. So if you have any doubts or if you want any further thing, you can comment in the video, or you can email me. Or who are preparing, who are doing MSc or who are preparing for CSIR UGC, available books are in the description. Please go through the description and click on the links. Finally, thank you.